Подожди, если я заношу.
Next speaker is Kristian Ranestad, and he will speak. The title of his conference is Cactus, Varieties of Homogeneous Forms.
Okay, thank you. Thank you very much. Thanks for the invitation to speak here. It's an honor this occasion. So, of course, I've known Fyodor for some time. His work was studied extensively when I was a student in Bergen in the early 80s. And then a few years later I got to meet him, and we had a good time together. So my choice of my topic was therefore something quite related, I think, to his work on higher secant varieties. So I need also only to apologize for some of you that have heard this before. Maybe you'll bear with me. So it's cactus varieties of homogeneous forms. And there is some collaboration with Bernardi, Yelisiev, and Marquez on this. So what is the setting? I'll use very much the same notation as the previous two talks. X will be a smooth variety, very soon more special, and I use this superscript here to denote the dimension, and now it's going to be in P big N. So this is a smooth variety. And but now already my notation differs a little bit. The secant variety I put this way, the rth secant variety of X. This is the union of linear spaces of dimension R minus 1. The dimension of the linear spaces is R minus 1, and I ask them to intersect X in R points. So that's now the number of intersection points. And then I close it up. Okay? That's my secret point. Well, my title says cactus varieties, not secant varieties. So what is that? Let me write it right away here. Cactus R of X. Well, it looks very similar. It's union of linear spaces of dimension R minus 1. And now I want the intersection of X not just be R points, but be a scheme of length R. Okay? And now I close that up. So this means that here the points may have come together. So there's some scheme there. The plane is, the linear space is intersecting the scheme in some points that come together. And it's not only the oscillating spaces we're talking about, it's more serious stuff. Okay. So my main question is the dimension. What is the dimension of the sequence variety? What is the dimension of the cactus variety? Well, this has been the study of Zach, among others, and there's quite a few things known about that, and in particular, in the case that I will soon get to, namely the varieties varieties. Well, this one here is much less studied. So my main issue is how they differ, when they differ, etc. Okay. So to understand that, if I take a general, there's a first lemma over here, which is due to drinking. I need the notes to get this right. And then the same with the E. E in the end. Yes. Well, it says if you take a general point in this cactus variety, general point, and then if you look at this scheme.
Is this variety reducible?
Very good point. Very good point. It's certainly not irreducible. Certainly not irreducible. Okay.
I mean, isn't the first one a component of the second one?
Yes. This one is a component of that one. So in general, this is far from irreducible. It's very irreducible. So still, yes?
The second variety is at least the second variety irreducible?
The second variety is, if X is irreducible, then the second variety is also irreducible.
So what do you mean by a general point?
So let's just take a general point in one of the components. That's good enough. Okay. So let me see if I get this right. Then X is in the span of some length Z. So length, there was R here, length R subscheme, where Z is contained in X, right? So if X is general and this C is a scheme such that X lies in the span of this scheme, it has length R and Z is locally Gornstein. Is locally Gornstein. It may have many components. In the second variety, it's just simple points. But in general, each component will be a local Gornstein scheme.
So, I'm sorry. So Z is going to stand at S at the general point.
So X,
Well, not Z. I mean, any component of the cactus.
X is certainly not on Z.
Yeah, sure.
Yeah.
Yeah.
But X is a general point. So this X is in the span of length R schemes,
Yeah.
but not in the scheme in the span of any length R minus 1 schemes. That's the question.
Sorry, it's R, not R minus 1. Thank you.
Yeah, I'm sorry for changing the notation from. Yeah.
Oh.
That's just okay.
So you're saying the zero scheme Z is locally Gornstein?
Yes. Yes, it's zero dimensional. It's locally Gornstein. So each component is a local Gornstein scheme. Okay.
Genetically. Because the points
So-
of X.
So you could even state it the other way around. You know, if you take a point in this space, if you take a point in this ambient space, and then you ask what is the minimal length of a scheme whose span contains X. If that minimal length is R, then every scheme of length R whose span contains X is locally Gornstein. If it's not locally Gornstein, then you can find a smaller scheme. That's the point. That's the observation. Okay. That was the first lemma. I think there are 3 lemmas in the story. This was really the first one. Okay. And so there is another lemma. Well, this is really a theorem by Kasnati, and Notari. And it says that any local Gornstein scheme of length less than 14 is smoothable. The finite scheme, length less than 14, then it's smoothable. This means that if R is less than 14, then these two are the same. Well, you can find a flat family where this is deformations. Yes.
It's sharp.
Is it sharp? It is sharp, yeah. There are non-smoothable schemes of length 14. Good point. Yes.
You mean smoothable in X?
Is it related to Graspinian to 6?
There are 2 questions here.
Is it related to Graspinian to 6? This non-smoothable.
Yeah, maybe. I don't know. I couldn't say. And here you say in X it doesn't. Yeah, also in X it doesn't matter. It doesn't matter because it's local. So that's why. Okay. So this means that when the cases that I'm really concerned with are really cases where R is big, at least 14. At least 14. So now,
But do you deform X in the deformation smoothable, or you deform your variety?
so you deform the variety, but you can deform the variety also in X. That's the point. Because it's local.
Yeah, so you can
Local
deform
shape.
X. Yeah.
So you can deform the variety. You fix X, and if the Z is in X, then you can deform it in Z in X. You don't change X. Okay. So now we go to projectives. spaces. So with that X, the X and D, which is VD of Pn inside P big N. That's a diupole embedding. We've seen this before, right? And in this case, just to compare things, the dimension of the, well, if D is bigger than 2, D is bigger than 2, then the dimension of the secant R secant variety of X, so let me put that again here, this is the minimum of, well, I just pick R points, R times N, and then you take N plus R plus 1, or minus 1, is it? It's minimum of this one and N. This is the result with 4 exceptions. I'm not going to list the exceptions, but there are exactly 4 exceptions to this statement when D is at least 2. Okay? So that, D is bigger than 2. So this is just underlined for the whole thing. Yes. Okay. Let me see. Let me compare this. I think I need to write it here to get the right size of this. Dimension of the cactus variety of R X. I need more space, I'm sorry. Yeah, so of course you could try to get the dimension of the cactus variety, the general cactus variety, but this I will not say anything about, but I will do it for 3, n equal to 3. So before that, I was jumping ahead a little bit here. So let me get back to the question, what is the minimal? What is the minimal R such that the cactus variety or the secant variety is equal to the whole space? And similarly, the cactus variety is equal to the whole space. And in particular for these guys, so I call this here R of X, and I call this here CR of X, for the cactus, CR of X. And from this here you will get that R of X n over D is just this big number here, which is n plus 2, n plus D over D, and 1 over n plus 1. Okay. And so, since I already reserved the thing on this side, CR of X and D is, and now we don't have a we don't have the. We only have a bound here. It's less than or equal to, and then 2n plus k over k if d is equal to 2k plus 1. So odd number. And if d is even, we get n plus k over k plus n plus k plus 1 over k plus 1. That's when d is equal to 2k plus 2. So just to compare these two numbers, I just write up the case when d is 3. And we are in this first case, and you actually get that this cactus rank, here, the other one, is 2 times n plus 1. While on this side here, you get r of x and 3 is n plus 3, n plus 2 over 6, when n is bigger than 4. So if you compare these two numbers, that's quadratic in n, and this is linear in n. And if you look at these two, this formula here compared to this formula here, you see that when you fix the d, then this is approximately, let me see, d to the n. Well, this is approximately here.
N to the d.
N
This is n to the d.
N to the d minus 1.
N to the d minus 1. Then it should be n half here. So this is n half to the d minus 1.
N to the d minus 1. N to the k is d minus 1.
N to the k, huh? So this means p over 2, approximately. Yeah. So that's the point. So you see when d grows and n grows, then the cactus variety is much, much bigger than the secant variety. Much, much bigger. So, and now I should also put in this number here. So here is Rn. This is not equality, it's again inequality. R times n plus r minus 1. That's the dimension of the that I had over there. But there is an extra thing. R times r minus 2 times r minus 16 over 48 minus 1. And there is a similar thing. This was the even case, and the odd case is similar. R minus 1, r minus 3, r minus 17 over 48 minus 2. So this is when r is at least 18 and even. This is at least 19 and odd. And you see this term here, r minus 16, r minus 17 coming into the picture. And that's those both 16 and 17 are more than 14. So there is room for something, right? But it doesn't really change before you get to 16 or 17. In 14 there is an extra component, but it's smaller dimension. But at these degrees, these r's, you get bigger dimension. So now to the proof of the general idea.
Isn't that the same problem that was as counterexample that Theodore just
It's
talked
a very
about?
similar issue coming up. Great. So maybe I skip this one also. So of course now I can think of this space here as a space of homogeneous polynomials. So I think of F, the point F in P n plus d over d minus 1. And so this is like P of C x0 up to xn, the degree d part. And inside here, x and d is just the powers of linear forms. Okay. Now, I have my polynomial f here. And I pick any linear form. I pick any linear form. And then I define L orthogonal to be the partials that kill L. Okay? It's the linear partials that kill L. It's orthogonal to the form L. And then I define a linear subspace in Pn. A linear subspace in Pn that's going to span the local Gornstein scheme. And I do it the following way, or I write it. It depends on exactly these two things, F and L. And it's the span of the following. L to the E of phi of F, where phi is the symmetric, in the E symmetric power of L orthogonal. So I'm taking partials, higher order partials, where I use the forms in this guy here, in this orthogonal. So I apply them to F. Since they have degree, this is E. The degree of F decreases by E, so I multiply again by L to the E's power to get back to the original degree of F. So this is a polynomial of degree D. It's a point in this space. So I should say like that. And I do this for all E, 0, 1, up to D. All possible. So this means that this is a space that contains F. When E is 0, and I get just F itself, it contains first order partials and then multiplied by the linear form, and all the way down to a constant. Take a partial of degree D, then you get a constant. And you multiply this by L to the D in that case. and there's your space. So this is the subspace, linear subspace inside Pn. And this subspace contains certainly that point. That's the only point that it contains on the variety. But it's oscillating in a serious way, this linear space. The intersection of this linear space with X, with the diopole embedding, with this guy here, is a local Gorenstein scheme, whose dimension, whose length is equal, or is precisely spanning this linear space. So it's determined by this, by the dimension of the space. So let me say that again. So L, FL, intersected with X and D. This is what I call Z, FL. And this is a local Gorenstein scheme supported at the point L to the D power. Okay. And the length of this thing is equal to the dimension of the space of partials of F, where phi belongs to this. So sim of L orthogonal. That's what I'm thinking here. Yeah?
I'm sorry, I don't quite understand. You mentioned that you started from F, which is a power of another linear function.
Yes.
Not of F, but another one.
Yes.
Then, as it is written in your formula, this point is also contained in this cell. Yeah? So the very first term.
Yes.
So which means that it may need more than, it is not necessarily supported at the point L.
But you claim that the 2 points are different.
They may be different. But at least the first point may be different from L.
It is the same point. If you take orthogonal, then L is the same point that you have started. So
there are two parameters, F and L. Just take F to be L prime to the power D. Then
yes.
Definitely F prime, definitely F is not L to the D.
Yes, you're right. You're right. I'm taking it back.
Maybe in this case, the last step is missing.
Yeah, there's something here. Then you would get L prime to the D, and then you get all the. You get all. Then you get the binary forms. All the binary forms. L generated by L and L prime, and that's just fine. Yes. So that's right. So there is a modification there. Thank you. Okay. So I'd like to think of this here also slightly differently, namely as the space, this length here as a dimension of the space of all partials of the form F. All partials of F, which is the original form here, but with L, put L equal to 1. So that's a dehomogenization. So let me write this. again over here. So if you have Z F X 0, then this is equal to the spec of Z D dx1 up to D dxn divided by F orthogonal, where F is the dehomogenization. And F orthogonal is just all the partials that kill F. So the differential operator. And now, so this was the homogeneous variant. Here is the more general inhomogeneous variant of this. And the statement is now that to get further, any local Gorenstein scheme, any local Gorenstein quotient of this ring is given by the quotient by some F orthogonal. So if it's a Gorenstein quotient, Artinian Gorenstein quotient, that is given this way. This is called Macaulay's inverse systems.
And is the converse also true? Is it true that for any F this quotient is Gorenstein?
Yes, yes. If F is homogeneous, then F determines this thing up to scalars. So so then F is unique up to scalar. If F is not homogeneous, then you have a bunch of different polynomials that give the same alpha. If you take F and add some partials of F, they will give you the same quotient. Okay. So the point here is that these cactus varieties, the worst cactus linear spaces, they touch then along schemes that could very well be of this kind. And our inequalities are just using exactly this operation here. And now, because the length is just computed, the length of this thing here is just the space of partials of F. Dimension of the space of partials. So, but that doesn't finish it, because we would like, of course, to make them dimension inequality and equality, try to show that the inequalities are sharp. And that's not, so these schemes here are not good enough. So that's what I'm going to do next. So there is a lemma. Maybe I can do it here. So suppose Z in X and D is a local subscheme, local Gorenstein scheme. So minimal with respect to the fact that F should be contained in the span of Z. Now, here I say local Gorenstein scheme. So this scheme is supposed to be supported at one point. Only one point. So then, by the statement I had just before, this scheme should be the spectrum of this kind. It should have exactly this form. Okay. Then Z is the spectrum of so assume so maybe the point x0 is there, so it's local at that point. Then I get d dx1 up to d dxn divided by some g orthogonal. So there exists a g such that z is this quotient and g is equal to f plus higher order terms. Okay. So there is a relation now between the g and the f, where f was, as before, the dehomogenization. I'm saying that that G that defines the scheme may be some polynomial, given maybe some polynomial of higher degree, but the lower degree part is f. Okay. So just to convince you about this is possible, I will finish with the simplest example. And that's, I take f to be x 1 squared x2 plus x2 squared. What are the partials of this? The partials are spanned by x1, x2, x1 squared in degree 2, and then there is x1 and x2 in degree 1 and 1 in degree 0. So every partial of this polynomial is a linear combination. It lies in the space spanned by these forms. Now I take G to be 1 over 12 x1 to the 4th plus or minus, I think of it. Plus here.
And what will be the second this example?
I'm sorry.
What will be this z which is defined on the top right platform in this example?
So if now I take f to big F to be the homogenization of this, right? And x0 is the point. Then this ZF at the point x0 will be a scheme of length 1, 2, 3, 4, 5, 6. And now I'm going to add this term here. I'm going to show that the space of partials of this polynomial is smaller. It will be supported at the same point, and it will contain f. I will not do the last part, but it's a higher degree polynomial, but it has fewer partials. And it's actually going to define a smaller Gorenstein scheme that contains f in its span. And this procedure, that goes on. So that's why you need something of this kind. So let me just do the calculation here. Here is the first guy, and then I take the partial of so the degree 3 part is 1 over 3 x1 to the third plus 2 x1 x2, and then degree 2 part I get x1 squared plus 2x2. That's the same I get by taking the partial with respect to x2 up there. So this is the only one in degree 2, and in degree 1 I get x1, and then I get the 1. So x2, for instance, is not the partial of this thing. And here I have 1, 2, 3, 4, 5, less than 6. So this happens. And that's why I need this thing here, and that's why we're not onto the sharpness yet. But if you do exactly the same thing for, so notice exactly as the question was here, we have your x. You can do that. You can do this thing for yeah. So I have x and d, right, and I have a point form f, and I'm for each L I'm finding for each linear form L. I find a scheme ZFL, right, with these two parameters. So if n is equal to 3, n is equal to 3 and d is equal to 3, then this is a cubic form defining a cubic surface. So this F defines a cubic surface, and L is of course then just a hyperplane section, a plane section of this cubic surface. For each of these plane sections, you can ask, what is the length of this ZFL? What is the minimal length of a scheme that contains F? So you see, in that case, that number will be almost constant, but not quite constant. When the section of the cubic surface is cuspidal, then you get a shorter scheme. For all the other ones, you get the same. But if it's cuspidal, you get a shorter scheme. So there's some geometry to it also. I think I should stop here.
Okay, thank you.
Questions? Not one question. So, coming back to the original question, the
Yes.
secant variety, the cactus variety.
Yes.
Can you give us the smallest example where the cactus variety is different from the secant variety?
Yeah. So I don't know this absolutely the first example, but the one example I know is if you take the triple embedding of P8, then the cactus variety will fill the space before the secant variety will. That's just these numbers that we had over here that we play with those.
Can you see the actual geometry of how that happens?
So this is the only thing, this is the only way I can, by describing these guys here. And the funny thing is somehow that, well, if you have a general point, then this, at least for these homogeneous varieties, then this local scheme that I produce, they all have the same length. And I expect that this is actually the minimum in these plots. So if you look at the kind of the fiber, so given a point, you know, what are the possible, then this is not going to be very interesting. It's going to be all over the place.
If you consider not just all schemes of fixed degree, but schemes supported at one point, deca union, will you get the same mode of growth?
Yes.
So that's
Yes.
so
So
you say yes. So this is should be compared rather with the creating spaces than with second varieties, because actually the main contribution comes from the points, 6 points.
Yes. But you said from tangent spaces, you say? Or
Oscillating. Also,
oscillating
which are
spaces.
form part of
Oscillating
them,
spaces,
part
yeah.
of them.
Part of them, because it's just in these linear spaces, they certainly cut all the oscillating spaces of different dimensions, but they also stick outside, right?
Yes.
Because they reach F, which is way outside.
Yeah, yeah.
Right?
But what can you say something about possible applications? Can you use this cactus variety for something? And they're highly reducible.
Yeah. So I don't know. So in a way, they have kind of a negative application because all the methods I've seen to compute the rank, which secant varieties your F lie on, all the methods there, they apply equally to cactus varieties. So they're bad. All those methods are bad when you go beyond 50.
Is this the point to introduce cactus varieties?
This is,
The reason.
yeah, this is the fragment, the first part, yes. But otherwise, I think they are very natural objects to study, because, yeah.
You said that secant varieties are some varieties of cactus varieties.
They're components.
Yeah.
They're components.
But in some cases you say that the dimension is larger.
So the cactus variety has many components, and the secant variety is always a component, separate component, because they are.
But sometimes it's also not a component of the highest dimension.
Exactly. In general, they are not.
Okay.
In general, these cactus, the other components of the cactus are much bigger, much bigger.
So one of the cactus varieties, the secant varieties, like Hilbert schemes to symmetric space.
Yes. It's exactly, the Hilbert schemes are much bigger than the smooth part. Right? That's really the idea. Right?
Yeah. Anyway, so do I understand correctly that in the definition of the secant variety, I only take the hyperplanes that all intersection points are transverse.
And I close it up.
Huh?
Yes. And I close it up. That's
yeah, then close, of course, but otherwise I would get to another cactus variety.
Yes.
Any other questions? If not, thank you very much. And look again at Sarah.